Well, today we're talking about running shoes and using biomechanics to understand design of running shoes, as well as using biomechanics to pick a particular running shoe. So when we start talking about running shoes, a term that comes up very commonly is energy absorption, shock absorption, impact attenuation. All of these are terms related to shoes. And if you go and look at shoes on the shelf, you can look at some and say, oh, that looks like it will absorb a lot of impact uh, or a lot of energy. And we need to talk about some of the mechanics behind that. Now, it's important to distinguish between energy absorption and force absorption. Forces are not absorbed. Forces are attenuated, they're reduced. Energy can be absorbed. But what do we really mean by energy? Because we know from physics that energy cannot be created nor destroyed, but it can be converted from one form to another. All right, so we convert energy from heat to nuclear or vice versa, or hydrodynamics or solar. Mechanical energy, we have potential energy, kinetic energy, elastic energy. There's all these different types of forms of energy, and we can convert energy from one form to another. And if we look at the amount of energy in a system at time one, it'll be the same exact amount of energy at time two in that system. It just may be different forms of energy. And so that's what we're talking about with shoes, is how what's happening when we say or use the term energy absorption, that a shoe is functioning to absorb energy. Uh, and why am I saying really it's not force absorption? Forces are attenuated. Uh, they are not absorbed. Okay, so let's go through that a little bit. So shoes energy absorption is a very common phrase to use. The way that I try to explain this term in shoe design is energy absorption really means reduction in kinetic energy. So remember kinetic energy, the equation is 1/2 mv squared. So we need to reduce the amount of kinetic energy when we design a shoe. That is, we're reducing how fast the foot is hitting the ground to where the foot is stopping from moving vertically. That reduction in velocity relates ultimately to a reduction in kinetic energy. And there's all different ways that we go about reducing that downward velocity at the foot strike of running. And so that's what, that in concept, that's what we're talking about when we talk about energy absorption. So let's go through some of the details on how we quantify the mechanics of a shoe in terms of energy absorption. So we do in the lab, we do shoe impact testing, and that impact test involves a particular instrument, impact tester, and this is a bad schematic of that impact tester. In the last video, I showed a picture of it from the manufacturer, and I'm just reducing that picture to something pretty simple like this. We have a mass that's connected to a rod, and that rod ends in what I would call a missile that's going to impact in this case, the test material, and the test material in this case would be the shoe. Now in this rod in the impact tester, we actually have some different instruments. For example, we may have a force transducer, and a force transducer is just a force measuring device. Okay, so we can actually measure forces during the impact, as well as the velocity of this missile and the acceleration of the missile. We can measure some deformation, things like that. I'll get to that in a second. So we have this missile part that contacts the shoe, and this is just a bad cartoon of the heel portion of the shoe. We do often test the forefoot region of a shoe, but most runners are heel strikers, and most shoes are designed for energy absorption at the heel, and therefore I'm really representing this as the rear portion of the shoe here. And this picture is drawn at the moment of impact, and this system will have a certain amount of energy that will be a function of the kinetic energy, a function of the kinetic energy, which is 1/2 mv squared. So 1/2 mass times how fast this is moving at the moment of impact squared. That will tell us how much kinetic energy there is at the moment of impact. And ultimately, the shoe needs to absorb that and reduce that kinetic energy to 0. That kinetic energy is transformed into some other type of energy, and I'll talk about that. So here is the moment that the missile, okay, this missile has deformed the shoe, and the velocity at this moment in time is 0. So we have maximum deformation in the shoe, the material has been compressed, and the velocity at this moment in time would be 0. And then naturally this shoe would uncompress, and it will push back up on the missile, and the missile will be lifted upwards and ultimately re-airborne. So it will bounce on the shoe. We're going to ultimately need to know this deformation here, how quickly it's deforming and how much it's deforming, to understand how this shoe or this material is actually behaving and absorbing energy. All right, so let's look at this here. So in order to get to that understanding, we need to know something about force and deformation of the surface that's being tested. So we got to remember work is force times distance, and the units, the base units of work are Newton meters, but that's not torque, okay? We use the units joules to represent work. Energy is the capacity to do work. Sometimes the way I describe this is I can apply a force over some distance. So I can do something, I can move something. If I apply a force and I don't move an object, then I'm doing no work, okay? It takes energy to do work. It takes energy to apply a force over some distance. So energy and work are very related mathematically and in physics. All right, so now I'm going to look at a force deformation curve. I'm going to draw this out to represent what happens during a shoe impact test. Remember, what we have here is a situation where the impact tester contacts the shoe, the missile contacts the very top of the shoe, and then ultimately compresses the shoe to some maximum deformation, and then it recoils. So this would be no deformation, and this over here would be lots of deformation. For a shoe, we may be talking, less than 1/2 centimeter. All right. For some test materials that are really soft, maybe we talk about as much as 5 centimeters. It depends on what we're testing. And here, this is the force applied from 0 force to more force. Okay. Now, when we record these data during a shoe test, we'll get data that looks something like this. That as we start applying more force, we start to get some deformation. And I'm going to draw it. The shape of this curve is dependent on how compliant or how stiff the surface is that we're testing. No, I'm not doing anything. I just did a bad drawing there. All right. The shape of this, how this changes, is dependent on the type of surface. But what we're seeing here is, as we are increasing force, we're increasing deformation. Okay, as force applied goes up, I'm getting further from this no deformation to some deformation. Okay, so this is during compression. All right. So the material is compressing, and I'm going to draw an arrow like this, meaning we're moving in this direction, or we're looking at this direction. That as we apply more and more force, we're getting more and more deformation. Now, what's interesting is, as we reach the maximum deformation, then we get the material starting to push back on the missile to push the missile upwards. So at this moment here, if I drop this down, this would be max deformation, and the velocity at this moment in time would be 0 meters per second. Okay, just conceptually, we should know that. This is the max deformation. Velocity has reached 0. Prior to this point, velocity would all be negative, and after this moment, velocity would start being positive. Now, I don't have time on this axis. Time is really represented by this arrow here moving along in this direction, that this is a later moment in time than here. All right, now, if I wanted to calculate the amount of work done by the missile on the shoe, I would calculate the area under this curve, okay? The area under the curve. I'm just gonna fill it in like this. I'm gonna write this here. Area under curve equals work done. How do I know that? Because we know work is FD, and how do we calculate area of this plot? We would calculate height by width. We would actually do this in smaller increments, but we have force here, and we have deformation here, or distance of the force being applied. And so the area represented here would be calculated by calculating how much force we're applying and how much deformation we have. So that's the work done on the shoe, by the missile. But now we've reached max deformation, and now the shoe is going to apply a force back on the missile. Well, it's applying a force on the missile the whole time, but now it's going to do work on the missile and move the missile back upward so the missile rebounds. Let me draw that, and I'm actually going to come back to that one here. So I'm going to redraw this so I don't get my graph too messy. I'm going to draw the same graph here as the one we're just dealing with. I'm going to put force here, and this is still deformation here. And now I'm going to draw that dotted line down here again. This is the same dotted line. This is the max deformation that we reached for this applied force. And now we're going to allow for recoil of the missile. It's going to bounce back up. All right, we're going to bounce back up, and what's going to happen is I'm going to get another curve that looks a lot like the first one. The shape of this curve is dependent on how elastic the material is. If it's really super absorbent, I may get a big drop in this curve. All right, and I'll show you. I'm going to put one on top of the other. I'm going to put arrows in this direction because time is not implicated on this graph, other than what we're doing is now we're collecting data as the shoe recoils and the missile starts to bounce upward. And as that happens, I start to have a reduction of force being applied to the shoe. That's this here. And I get a reduction in deformation. The material starts to go back to the original shape. All right, so eventually we get back to the same point. So this is recoil. All right, I could calculate the area under this curve as well using that same equation, work equals FD. All right, so now let's put these two together, and I'll do the best I can. I'll draw the graph out again. Force, deformation, and now I'm going to draw the compression of the material here. Okay, compression. And again, time is implicated on this as we're going in this direction. We're applying more and more force. We're getting more and more deformation. We reach the max deformation, and then the missile starts to move upwards and the material starts to recoil or go back to its original shape. So we get that. I'm going to put arrows here. and this is recoil. Now, remember we said we can calculate the work under the original curve, and we can calculate the work in the other curve. The work under the original curve is the work done on the shoe by the missile. The work under the second curve, the recoil curve, is the work of the shoe on the missile, pushing the missile upwards. So the difference between the amount of work done by the shoe and the work done on the shoe is energy absorption. And that's this area in here. I'm going to try to draw that in a little bit, shade that in. Energy absorbed. And I'm putting that in quotes because energy is not really absorbed. It's just transformed into something else. Maybe heat, maybe some of this is elastic energy, maybe it's something else, sound, who knows. But we know that, from this relationship, the difference between these two curves, the compression and the recoil, is the amount of energy absorbed by the material. Now let's think of a material that does not absorb a lot of energy. What would that be? That'd be a very stiff surface. So cement, all right? In cement, this is, I'm not going to draw it accurately, but just to get the idea, I'll put force here, I'll put deformation here. A stiff surface, a rigid surface, I would have very little loss of energy between compression and recoil. Remember, this side is compression, this side is recoil. Now let's say I take something like a ball of clay and I drop a missile on a ball of clay. Think about that. The missile would hit the clay, it would compress the clay, but there would be no recoil. All right, so I'm going to put force here, I'm going to put deformation here, and I'm going to put compliant surface. And now I may have a curve that would look something like this, and then something that absorbs a lot of energy would be like this. So again, we're going in this direction in time, and this is compression. And this is recoil. Okay, compression. It's compressing, a force is being applied, we're having more deformation, but then once the material is compressed, it's pushing back upwards on the missile to move the missile upwards, because we're going to have max deformation here, we're going to have zero velocity. Now the velocity is going to start being directed upwards of the missile, and it's going to recoil, but it's not generating a lot of force to allow for that recoil, and that missile will not bounce very high, if at all, depending on how compliant the surface is. All right, and the area in here represents energy absorption. Energy absorption. Sometimes I spell that with a P, sometimes with a B. Little energy absorbed, because there's a small area in there. Lots of energy absorbed. Right? And this is the type of data we would get out of a shoe impact testing device. All right, this will be my last set of notes here, I think. Here's just another way to sort of think about all this and some of the physics behind it. I have some mass. Think about a ball dropping onto the shoe. Just think about what would happen if you take a bowling ball and drop it on the shoe, and let's say you drop it from some height. Would that bowling ball rebound to the same height? Okay, well, it would if all the energy is returned by the shoe. But the energy is typically not all returned, and the ball won't bounce as high afterwards. So we just get to that height. This would be height through, oh, I got time down here, time 1, time 2, and time 3. All right, so this is just looking at the height here. So let's say that this mass comes down, hits the shoe, and we have some deformation here of the surface. All right, this deformation here would be the same deformation as I'm looking at here. Okay, that represents how much deformation this material is undergoing. That's the same amount of deformation, just looked at from a different illustration, different cartoon, if you will. Mark is not doing good. So what do we have here? We have the shoe absorbing energy. Energy is transformed from mechanical kinetic energy to something else. In this case, by this point, it's converted to elastic energy because there's some spring characteristics to the surface, and that's going to return the energy. So we really have energy absorption, then we have energy returned back on the missile, and the missile, or in this case the ball, bounces back up. All right, so that's a little bit of overview of impact testing of shoes. If we look at energy absorption, we're really talking about the reduction in kinetic energy, and then energy absorption is also really a function of how much force is being applied to deform something, and then how much recoiling is allowed by that material, and work being done back on the missile. Okay, thanks everybody.